Today, we're going to be talking about async and futures in Rust. So what is all this? What is async and futures in Rust? What is the point? When you boil it all down, async in Rust is an abstraction that it provides to express concurrent units of work. So we're talking about units of work that can operate at the same time as each other. Maybe that means threads. Maybe it means something else. All we care about is that they are concurrent. A future is sort of the building block of the whole thing, and a future is a single unit of work that can operate concurrently with other futures. You should always be coming back to the idea when you're getting confused about this stuff. Async await. So we talk about like async functions, async blocks, awaiting, the await expression. Async await are syntax primitives, language primitives that interact with futures and lets you build up bigger futures and use futures in a style that reads very naturally. But they are sugar for just the futures again. Almost always when we're talking about async, we're talking about async IO. So we're talking about building like big servers that can handle thousands and thousands of connections, all concurrently. We're talking about pretty much just that. That's the big one. But it's important to know that the model that Rust exposes is not limited to IO. IO is just the most common expression of it. For that reason, we are not talking about Tokyo mostly. Tokyo is just a library that builds up on top of these sort of really core fundamental abstractions that Rust gives us. So future, that's the building block. Let's talk about a future. This is what a future looks like. This is the trait. There's a few different moving parts here, and we'll go through them one by one. A future has an output type, pretty straightforward. This is what it tells you when it's done, right? So if it's a network request that's getting an image, probably the output type is going to be your image. It's got a poll function. The poll function is where the work gets done. This is where, if you have an async function, the poll method of the trait is where the body of the async function is executed. Poll functions take self by pinned reference. I'm going to try to avoid talking about pins as much as possible because it's not super relevant, but it is important because they are sort of viral to the whole thing. Like when you have a pin, it tends to infect other things. A pin is a type of mutable reference to something. Specifically, it's a mutable reference that requires that whatever is being referenced is not moved. Whatever is in that reference has to stay there until it's dropped. It's difficult to use safely because this promise, this must not move promise, persists even after the pin is dropped. Once you create a pin to something, it must remain pinned for the remainder of its entire existence, even when the pin goes away. For this reason, they're very challenging to use safely, but there's going to be a lot of libraries that we are going to use to make that easier to deal with. The poll function returns a poll object, which is essentially another kind of option. The poll object, the poll enum, tells you either that we're done, and the thing is we have a ready result, right? We have an output, we're done. We got what we are looking for. Or it returns pending. Pending means that we are going to need to be polled again in the future. We've set up some sort of work. You know, we're waiting for a sleep, we're waiting for IO, we're waiting for a socket, and we are going to need to be polled again at some point in the future. The obvious question is, when are we polled again? How do we know when to be polled again? And the answer is in this context. The context contains a waker. We have a context separate from a waker because there's this idea that in the future we might add more things to the context. But right now, a context is really just a vehicle for this waker. A waker is a struct. You can make your own wakers. And a waker has these wake methods. So the idea here is that when you poll a future and the future needs to block, right? It needs to do some long work, like waiting for a sleep or waiting for a socket or something. It returns pending, but before it does so, it arranges somehow, unspecified how, it has arranged that waker.wake will be called when we are ready to be polled again to try to make more progress. In return, the person who called poll has promised that they have provided a waker that they are scrutinizing, right? So the caller of poll, when the waker is awoken, the caller of poll will poll again. That's sort of the fundamental dance. Everything else in async actually just arises from that one core idea. You poll the future, it returns pending. It has arranged to be awoken when it wants to make more progress, and the caller has arranged to call it again when it wants to make more progress. You can poll futures spuriously, so you might get polled again even if you didn't awaken yourself. Typically, this happens because sometimes many futures will share the same waker, and so if one of them gets awoken, they're all going to get polled again. This means that just calling poll in a loop with a no-op waker is technically a valid implementation of this, right? You can just keep calling poll forever, and it keeps doing nothing forever until it finishes. The other thing that's cool here, though, is that you can just not poll it again. If you are done with this future, if like the connection was dropped, or you timed out, whatever it is, you can just not poll the future and drop the future, and whatever work the future was doing will not make any more progress. This sort of becomes the difference between a Rust future and a JavaScript promise. A JavaScript promise, when you kick it off, it's going, right? You have handed it off to the runtime, and the runtime is running the promise, and it's sort of out of your hands. On the other hand, a future is totally inert. A future does not do anything while it exists. It makes progress in the poll function in the foreground. When you call the poll function, the body of your async block is executed. This is the one that I want to keep coming back to because it is sort of, it's the thing that I think is most surprising if you're used to JavaScript. Calling an async function, all that does is give you a future, and the future doesn't do anything unless it's polled. Now, I can sort of hear the confusion back there. You know, we have polling and wakers and all this, and this doesn't resemble what we think of when we think of async, because we think of async blocks and awaiting. Async blocks and async functions just build on top of this idea. An async block is just a block that creates a type or creates an object of some type that implements a future. An async function is just a function that returns some kind of object that implements future. It's very, very similar to like a lambda, right? Like the double pipe function object. Just creates some kind of object that implements the function trait. The future that's created, the future type that's created by this, when it awaits something, you can await any future. When it awaits a future, that just means that the poll function that was created polls the inner future. And when the inner future returns pending, the async function returns pending, and it has state. It remembers where it was last awaited, you know, including like where in the for loop it was, where in the ifs it was. All the control flow stuff is preserved. Excuse me. And when you poll it again, it returns to where it left off, repolls the inner future, and continues. That's the basic idea. To show this off, we are going to be writing a very basic function that runs a future. We're going to write a function that runs a single future to completion, just to show how this polling and waker business all fits together. Let's check it out. All right. So we are going to run a future. Great. Running a future. Here's our future. And we are returning whatever the future returns. Great. We know we have to poll it. And we know that the first thing we saw was that it requires a pinned reference, whatever that means. For us, we're going to use, there's a great little macro here called pin mute, which pins something to the stack. This takes care of the unsafety, right? This guarantees that whatever we have pinned is pinned forever. The way this essentially works is that it takes our object and shadows it. So it uses the same name, shadows it with a pinned reference. This means that it's not possible to get at the original object ever again, which means that we can't ever violate this contract. We can't ever accidentally move this object because we've lost access to it through here. All right, so we want to poll the future. We need to give it a context. So let's make a context. And we're going to come back to this in just a second. We'll just have the context there for now. But first, the simple stuff, what happens when we poll it? Well, there's a few things that can happen. We've got, it could return ready, poll ready. That means we're done. Great, easy. The other thing that happens is that we're pending. Okay, so let's think about this for a second. When this poll returns pending, we're not providing a runtime here, right? We're not providing any other, we're not providing sockets or timers or anything like that. We are just running this future. This future has promised us that when it returns pending, it has arranged for the waker inside of this context to be called when it wants to make more progress. So all we have to do is just block the thread. We're going to use the classic old school mutex and condition variable. If you're writing like a real one of these, which you probably won't be because you're just going to use Tokyo. But if you're writing a real one of these, you're going to use something more efficient. But for our demonstration purposes, we can just use the classic old standbys. Notifier. So we're going to have a mutex in here. Was notified. Notify. And we're going to have a condition variable in here. Condition variable. All right. So there's two halves of this, right? We need to be able to sleep, block the thread waiting for this to be signaled, and we need to be able to make a waker out of this so that we can signal, so that our futures can signal it. We'll do the blocking part first. So we'll impl notifier. Pretty straightforward. We're going to lock the mutex. Let was notified. Self.wasNotified.lock. And then we are just going to wait for that to be set to true, right? So while that's false, we will have to make this mutable. We will wait on our condition variable for a signal. The condition variable takes the mutex and unlocks it so that it can make progress, and then it'll relock it when we're done. Then we'll set it back to false, just so that we can reuse it in the future, so that other futures can notify us again. Great. I think we need an unwrap here. That's what I'm missing. Great. So we can make our notifier. Let notifier. Okay. And we can wait for it. Great. What do we want a semicolon here? We'll come back to that. The other half of this is a waker. Much like pin, making your own wakers is sort of a pain. It involves a lot of unsafe. It involves a lot of like raw pointers and function pointers and so on. So once again, we're going to use a library. We're going to use a library that I wrote called cooked waker. This is called cooked waker because normally the type that Rust gives you is called a raw waker. And so a cooked waker makes a raw waker safe for consumption. So we're going to impl wakeref for notifier. And we are going to figure out why Rust Analyzer doesn't like us anymore. Impl wakeref for notifier. Oh, waker ref, that's the problem. There we go. We hit the condition variable, right? So we're going to say lock the mutex. Okay. We're going to set this to true, and we're also going to return the value it was previously. We'll say that if it wasn't already notified, then and only then will we signal the condition variable. So we'll say we'll put a true in there, and replace will return the old value, which we will get here outside of the lock. That was notified equals all that. Great. If we weren't already notified, hit the condition variable. Self.cv cv.notify1. Great. So notifiers can be awoken. Now we have to share this. We have to have our own copy of it, but we also have to share it with the future inside of this context. And for that, we can just use an arc. Almost all wakers, like 99% of wakers, are just an arc to some sort of structure like this. And the reason is that wakers need to be cheaply clonable, because many futures might take their own copies of wakers to manage their own logic. So that we pretty much always put them inside of an arc. So we will do that. We will put this in an arc. Okay. We will go ahead and get our waker out of it. So we will create another one of these. We'll say notifier.clone. Cool. And then we are going to turn that into a waker, which comes from this into waker trait. So this function here manages all of the horrible logic of creating like raw pointers and function pointers and dealing with all that stuff for us. We have our waker. We can now put the waker inside of our context. Let's see, x equals context from waker. And we can put this thing in here. And I'm still wondering where the semicolon I want. Oh, we have to put a match. Let's see what I did here. We have to match it. I'm so sorry. There we go. And then finally, obviously, we need to loop over all this, right? So we're gonna put this in here. We're gonna say we're gonna loop it. We're gonna loop it. Great. Move value here. So this is yelling at us because a pinned reference is not a regular mutable reference. So when you call a function on it, it's essentially a move. So future provides an asmute function, which essentially is like it's kind of like a copy, but with a shorter lifetime, which takes care of the moving issue. Let's dot poll this. Let's make this mutable. And there we go. So this is it, right? I mean, this is what, like 50 lines of code, and that's mostly like imports and boilerplate. What I've written here is like half of what Tokio does. What Tokio does is more efficient and more complex. It has like all kinds of extra stuff that it offers. But at the end of the day, Tokio is creating a context, creating a waker, and then polling futures. Oops, let's get out of here. We can see this actually in practice. We can just make a little async function here that does very little. Actually, here, we'll do this in main. And we will go ahead and export this instead. There we go. All right. So we can write a little async function here. Async function simple, returning 10. Great. Here in main, so here's where we're going to see the point of all this, right? An executor, this function that runs a future, serves as the bridge between the sync world and the async world, right? In the async world, we have non-blocking, everything's awaiting everything else. And at some point, at the very sort of bottom of the stack, at some point, somebody has to start polling all this and waiting for it to finish synchronously. That's what an executor does. So we can say, let fut equals simple. Again, we've called an async function, but this is an inert future. This doesn't do anything except for sit here and wait to be polled. We will run it. There's our function. And we can see that this will succeed. There we go, success. We can make this a little bit more fun. So we can actually we can show an await in here. So we're gonna make our own future real quick. We're gonna make a super trivial one that just returns pending once, immediately notifies, and then returns ready. So we're gonna go ahead and make a yielder. Yielded is a bool. And we will impl future on it. Okay. We're going to output nothing. We're just going to say it's either done or it's not. And in here, it's going to be really simple. If we haven't yielded yet, we will say, okay, we've yielded now. Self.yielded is true. We will immediately notify the waker, right? .wake by ref. This is sort of the key here because this tells us that we have to immediately poll ourselves again, and we return pending. Right? If we were already pinned, if we were already polled, we can say we're ready. Poll ready. We can make this mutable. Great. This is a future. All futures can be awaited. So in here, we can say, let inner equals, we'll say yield with false. And then we can await it, inner.await. Any future can be awaited. And again, all that's happening here is that this function is returning some sort of future object that has its own poll function. When we hit this point, it's going to poll this. When this returns pending, this returns pending. And it remembers this is where we left off. Next time we poll, we're going to jump right back to this point and continue from where we left off. We will see it. This still works again. Great. And as one final little thing, we can actually throw some prints in here just to show off how that this is working. So we'll say impl waiting for notify or waiting for wake. And then down here, we can put a semicolon. And then down here, we can put one of these. We can say awoken. And so we will see when we run this that it gets awoken right away and continues, right? It never had the opportunity to wait because we immediately woke it up. So it just gets awoken once and finishes. All right. I know that was sort of a lot. Are there any questions at this point before I jump into showing a more elaborate future? No? All right, great. So what I want to show you now is a more elaborate future. I specifically want to show you a future that sleeps, right? The classic sleep function. But in this case, it's going to be an asynchronous sleep. So think for a minute about the requirements here. So we'll call it a delay. And we know that it's going to sleep until some deadline. Okay. So think a little bit about the requirements here. We have to return pending and then awaken the waker that we got when our timer expires. We have no runtime, right? We're just going to use that same executor we saw before. So we have to take care of it ourselves. We could just spin loop, right? We could do what we did before, awaken ourselves constantly check the time and eventually wake up, but that would be silly. Which means that we probably need a thread that can actually, in a blocking way, go to sleep. Now, it would be very silly to have every single one of these features create its own thread that just goes to sleep. That would sort of defeat the entire purpose of the whole async idea. But what we can do, think about it, suppose this is a library that we are publishing. We can have one global thread that this library provides that stores every single timer in it. It puts it in a binary heap, so it's always sorted, and tracks, which timer is attached to which waker, awakes them all as they come up one by one, has a channel to listen for, incoming new sleeps, and generally just sort of runs the whole thing in a single thread. That's what we're going to make. We'll start with the sort of interface that we're going to write, and then we'll fill it in later. So we will say sleeper thread channel. So we know that we have a global thread that's just going to be running, and our interface for it, our way to talk to it, is going to be a channel. So we will say this returns a static reference to a sender. Excuse me. We are going to be sending messages to it. We'll be sending messages to it. So we'll say message, and we will see as we write what actual messages we are going to be sending to this thing. But for now, we can just be content to say that we are sending messages. Okay, we'll come back to this. So we have our delay here. Let's go ahead and write our quick little interface for it. We will say we have a sleep until pub function sleep until some moment in time. And then, of course, our classic old sleep function. Same thing. But this sleeps until now plus the duration. Okay. Even though these aren't tagged as async functions, these are functionally async functions. It's a function that returns a future. So we can just call, sleep duration dot await, and we'll see that once it's all done and ready. Okay. So we need to impl future for delay. Like before, we're not returning anything. We just want to know when it's done. Okay. So let's think about what we're doing here. The first time we poll, we have been given a waker in this context, and we want to tell the thread from earlier, this thread here, that we have this waker and we want to let it know here's when we're done. So that sort of forms our message, right? We have some deadline, we have some waker, and to avoid potential issues with clock sync between threads, and this thread thinks that we're slightly in the future from this other thread, which unfortunately can happen. We're going to use another channel to sort of synchronize everything. So with this channel, the sleeper thread will use this channel to let us know when our timer has expired, when we're done. Okay, so we've been polled. We need to create this channel. We'll call it notify on this end and signal on this end. We'll just make it a bounded 1 because we know we're only ever going to get one message out of it. We will make our message where we have our notify side. We have our waker. It's in the context, cx.waker.clone. This cx.waker returns a reference to a waker. So 90% of the time, you're going to be cloning it. And we have our deadline. Okay. Notice that we are not checking the time here. We're sort of assuming that most of the time, the first time you poll the future, it will not be expired yet. So it doesn't really do us any good to check the time immediately. We might as well just always do the round trip through the sleeper thread. We will send this message to the sleeper thread. And because this is a static reference, the thread should never die. This should never be dropped, which means we can just unwrap it here. Okay, great. So at this point, we've sort of fulfilled the first half of the promise, right? We have promised that when you poll the function, we are going to sleep and we are going to signal this waker when we are ready to be polled again. Now, we are going to need some sort of state here. Actually, let's return pending real quick because that's sort of the last half of it. Pending. Great. Now, we need some sort of state. We need to save this signal so that we can check it in the future. So let's go ahead and do that. We will make ourselves a state. We will say enum delay state. And either we are fresh, brand new, don't have any state, or we're waiting. If we're waiting, we have a signal, which is a receiver. Cool. We'll go ahead and put this in the delay. Cool. And we will put this right here. It's brand new. Delay, the state is new. Great. Now here in our poll function, we can check our state. Once again, pin comes back to bite us in the ass. We can, because none of this stuff in here is sort of, in here is sort of pin sensitive. This is all sort of just regular plain old data stuff. Pin can detect that through a trait called unpin, and we can use a method called getMute equals self.getMute. That turned us back into a standard mutable reference. And we can do this because we're sort of guaranteed that nothing bad will happen if we unpin ourselves like this. So now in here, we'll say this is this.deadline. We'll go ahead and set our state. Cool. And now in our poll function, we will actually match on this, right? So we'll say, we'll get our this, and then we will say match this dot state. Okay. If we're new, well, we just talked about that. That's all this logic. So we'll take all this, put it in here. Great, no problem. If we are waiting, okay, so we've been polled again. It might have been spurious. We're not guaranteed that just because we're being polled that we are ready to, that our timer has expired. So we check our signal to see if we are, excuse me. We check our signal to see if we're done. We will try receive. It's critical not to block here. And we will go ahead and match on this. If we are done, right? If the thread sent us a message on our signal, great, we're done. We are actually done. We can return poll ready. Timer's expired. Everything's great. If we are not done, there's a few different reasons why we may not be done. We could be disconnected. Disconnected means that the thread dropped us. This really shouldn't be possible. The thread should not be dropping us unless we are actually done. So this actually does warrant a panic, even though in practice it should never happen. Because our logic ensures that doesn't happen. And then the other thing that's going to happen is that it's empty. This is the typical case, right? We were polled, but we weren't ready yet. We do have sort of a problem here. And the problem here is that when we're polled, there is no guarantee that we were given the same waker as before. Usually we will be, but we can't guarantee that we were. Futures don't have to keep track of every waker. You only ever care about the most recent one. what this means is that we actually need to send another message. We need to let the thread know we might have a new waker. A more efficient, like, a more elaborate, more efficient implementation might like store the waker locally, because you can check if two wakers are the same. But for simplicity, we are just going to always send it. So we'll say polled. We got a new waker, maybe. Cool. So let's go ahead and send this waker. We'll go ahead and make another message here. Great. Go ahead and send it. Great. And we are still pending. We're still waiting. We have still upheld the promise. Okay. And something has been moved. What's going on here? This, I think I put a self somewhere. This needs to be a ref. That's the problem. Great. Okay. This is a complete future. I mean, obviously we need to implement this to make it all work, but this fulfills the promise, right? We got a context. The context had a waker. We have independently somehow set things up such that the waker is awoken when we're ready to make more progress. That idea of being awoken when we're ready is called a reactor, right? Because it reacts to events. So it reacts to timers expiring. It reacts to almost always I/O events, like a socket being ready to read in a networking application. And a reactor is the other half of Tokio. I mentioned earlier that the executor was the first half. The reactor is the other half. So when you're talking about Tokio, you're talking about small or async STD. You're talking about async runtimes. You're talking about a library that provides an executor and a reactor, and primitives that interact with them, right? Because what we've done this with threads, right? We have made an executor that just always goes to sleep, and we have made a reactor that lives in a separate thread. A real one like Tokio has the ability to combine them into the same loop and do everything sort of thread locally. But that's all that's going on. We are polling futures, and we are internally arranging for wakers to be awoken, when an epoll completes or when a timer expires or whatever. All right. Speaking of reactors, let's go ahead and write our reactor. Let's move it down to the bottom. Okay. So what are we thinking about here? We are receiving messages. So let's go ahead and set that up. We're going to make a global static channel. Channel. This is a static. Static channel is a once cell of senders of messages. Okay. The first time we call this function, we will go ahead and initialize this. We'll say channel.getOrinit. Okay. We will build our channel. We're going to use an unbounded channel here. So we're going to say, let sender receiver equals unbounded. The problem with the unbounded channel is that it could, grow without limit if we sleep a lot. What we should be doing here is using a bounded channel, but with a bounded channel, we might block here in the poll, which means what we should be doing is using an async aware bounded channel, which just means that it's a channel that is aware of wakers, right? It's the same idea. If you try to push to a channel, but the channel is full, you have to return pending. The channel has the waker. And when the channel is not full anymore, right, when something is popped off the front of the channel, it wakes up, it calls wake, which means that the future will be polled again, and we're going to attempt again to add something to the channel. That's sort of the key difference when we're looking at like a Tokio channel or a futures channel versus a standard library channel or a crossbeam channel. The difference is that they're async aware, which means that they operate with futures, which just means that they are sort of waker aware. They can be polled and they can return pending. Once again, though, for simplicity, we're not going to do that. We're going to assume that we have enough sleeps or a reasonable duration of sleeps that we're never going to overflow this channel. All right, we've got our sender receiver. Let's go ahead and spawn a thread. We'll say thread spawn. We'll come back to this. And here's our sender for the channel. Great. Okay, so we've got our sender. It gets stored in this channel and it gets returned here. So now we can write our thread. All right. So just to reiterate again, the whole point of this thread is that as we create all these delays, every time we poll them, they're going to be sending us messages that we need to respond to. So we need some data structures. We will make a, excuse me. We will make a binary heap to store the timers themselves. We'll say let timers is a binary heap of a instant, but binary heaps are max heaps. When we pop off a Rust binary heap, we're always gonna get the biggest one. And for our timer, obviously we want the smallest one. We want the one that's soonest. So we will use a convenient little helper here called reverse, which just reverses the sort order of whatever you put inside of it. And we need something here. We could put the waker here, but the trouble is that if you recall that we might get new wakers, we need some way to set new wakers in here. And we can't really modify something that's in a binary heap once it's in there, which means that we need some way to identify delays. We are going to use a library called Snowflake for that. Snowflake is a lovely little thing that provides process unique ID. Process unique ID is a ID that is guaranteed to be unique within your process, right? So it isn't a UUID. It isn't like globally in the entire universe unique, but it's guaranteed that within the duration of a single process, it will be unique, and it can get away with being extremely fast because it just uses like thread locals and atomics to produce these things. We will store our ID in our states. We will say ID is a process local ID. Cool. We will go ahead and make one of these the first time we get polled. Let ID equals process local ID new. We will put it here in the state. And we will put it here in the message. And we'll go ahead and make sure that's in the message. Put one there and put one there. Great. We need it here. This is where we're going to start to see Rust helping us out a lot, because we're going to be dealing with a lot of like sort of edge cases with errors that have different kinds of failure modes. And because match is comprehensive, it's sort of going to help us guarantee that no matter what we do, we have taken care of, everything that needs to be taken care of. So here in our thread, we have our reversed thing. We're going to go ahead and put a ID in here because we know we have our process message ID. Cool. And we will not forget something. Oh yeah, there we go. And we will associate these IDs with our wakers, right? Wakers is a hash map from ID to a waker and our sender. You'll recall that we had in our message, we used a channel here to synchronize when a particular deadline expires without having to worry about clock sync issues. And we will go ahead and actually make these. Hash map new. Binary heap new. Okay, great. All right, we have our data structures. Now we're just going to loop forever dealing with messages. Let's go ahead and wait for a message. We'll say let message equals match receiver dot receive. Okay, so now here's sort of the key. We need to listen for a message. We need to sleep the thread waiting for a message until the timer expires. So either we are receiving with a deadline or we are just receiving, which means that we need to know how long to sleep for. So before we do this, even though on the first iteration of the loop there's no timers, we're going to set it up so that we check for it anyway. We're going to say let next event equals loop. We're going to loop over all of the timers because we want to make sure that every single timer that has expired is dealt with. We'll say let now equals instant now. Cool. We will say match timers dot peak mute. Peak mute is a great little method on binary heap. Essentially, it's a peak, but it has the ability to also pop off the heap in a way that doesn't return an option. It's just very convenient in that way. So peak mute. If the timers are empty, great. We know that there is no next event. We can break out of our loop with a none. We know that when we are listening for messages, we can listen forever. We're not waiting for any event. If we got something though, okay, let's go ahead and check real quick if it's in the past, right? So if slot dot 0, that's the reverse instant. Dot 0 again is the instant inside of the reverse. If that is in the past, right? If that's less than now, we deal with it. we're going to look it up in our wakers table. We'll say if let sum waker sender equals wakers dot remove this ID. This is going to be slot.1. We will try to send to the sender. We'll say sender.send our message, right? Because this is telling that particular delay that its timer has expired. If the delay was dropped earlier, well, then this will fail because the channel was closed. So we can use that to determine if we should awaken anything, right? If the delay was dropped, there's no reason to ping this waker. But it probably wasn't, so we can wake it right here, waker.wake. Great. If the next nearest timer is in the future, cool. We know that that's our maximum duration. We're listening for messages until that timer expires. So we will break out of our loop with that, sum slot.0.0. We'll close all this out with a semicolon. Okay. We will make our data structures mutable. That's sort of important. Cool. So we've handled all of our timers, and we know when our next event is, if there is one. So we will say match next event. If it's infinitely in the future, we can just say we're going to get a message. So here's where we're going to retrieve our message from the channel. Let message equals. So we'll say receiver.receive. The only reason this should fail is if the sender was dropped, but because the sender is static, it can never be dropped. So we can reliably unwrap this here. Okay. If we have a deadline though, that's fine. We just have to receive on that. We'll say receiver.receive with a deadline. Receive with a deadline. Got a message. Great. There's our message. There's a few different ways this can fail, right? If we got a timeout, that's fine. It means that we didn't get any messages, but one of our timers has expired. So we're going to go ahead and start the loop over. Cool. We're going to throw this here just to make roast analyzer happy. Finally, if we were disconnected, again, this shouldn't be possible because the only way to get a disconnected error is to have this sender be dropped, which can't happen because it's static. So we can just put we can just do a no op here. We can actually do a panic here. Sender. Great. We have a message. We can handle the message. Match message. And you can sort of see how our matching and all our comprehensive pattern matching is enabling us to not miss anything by accident. All right, two kinds of things can happen. Either a new delay was created or an existing delay was pulled. This one's super easy. We just add it to the table, right? We're gonna say timers.push. We mentioned earlier that we're using a reverse. Just make sure these are sorted correctly. Reverse deadline. And our ID. And wakers.insert. Our ID and our waker and our notifier. Great. If we were polled, it's very similar, but we have to look up our thing in the table, right? We're going to say if let sum waker and don't care equals our table, wakers dot get mute ID. Cool. Waker is now our new waker. We'll call this old waker. Old waker. Star old waker. Great. One last thing that I realized I missed here. Here, we need to make sure that we also expire the timer, right? So if this timer is in the past, if we're triggering it, we need to make sure we get it out of the table. So we're going to go ahead and say let don't care and our ID equals peak mute pop the slot. Right. So if we're in the past, we go ahead and pop it off of this. We go ahead and pop it out of the out of our binary heap. Here we can use our ID directly. Great. And that's it, right? We have now fulfilled the other half of the promise. We have arranged in this future that when it's polled, the waker will be triggered when we want to poll it again. And we can go see this in our executor. So let's swing back around here to main. Let's add a sleep now to this function. We'll keep our yield here because it's kind of fun. But before that, we will say we have our sleep module. We will sleep for say we'll say 5 seconds. From secs 5. This is a future. We can await it, right? So all that work means that we can just write this await here and just await from the sleep, right? And we should see this runs. We should see that it sits and does nothing for 5 seconds. We see that our executor is printing its notifications, as it runs. It'll be notified, and we're done. Okay, so we have our sleep. We have our basic future, and we have a way to run individual futures. It's still not a full runtime. We still can't run like a whole lot of futures, except that because of the way the futures are designed, because they are idle until polled, they are super easy to compose together. And that's really what the futures library is all about. It gives us a lot of great primitives for combining futures, right? So if you want to .map a future, easy. You create your mapping object. It's a future. It contains the function, very, very similar to an iterator. If you want to .then, right? Same thing, just like the iterator's flat map. Or if you want to run 2 futures at the same time, you just poll them both, right? You poll the first one, it returns pending or ready. Poll the next one, it returns pending or ready. They have now both arranged their own work independently, however they do it. And we are waiting for both of them at the same time. We can see that here. So we'll say let sleep 5 equals that. We will say let sleep 3 equals sleep for 3 seconds. Okay, and we will use join. Join just takes 2 futures, puts them together into a new future that when it's awaited, it awaits them both. It polls them both. Await. What we should see here is that this is going to wait for 5 seconds again, right? Because this one will finish, and then this one will finish. But we'll see a couple more awaitings here, as the first one will trigger, this future will finish, and then it'll keep waiting for this one. So we'll run it. We should see in about 3 seconds it pings, and then 2 more seconds, and we're done. This idea right here is where I really get excited about futures, where I really am like, this is really, really, really cool. No offense compared to JavaScript. Because of this polling model, and because you can, because futures are idle, they can be freely and easily combined like this. I have one last thing to show before I take the final questions, and and I hope that this sort of drives home how cool this is. Okay, let's come back here to our sleep. Suppose now that we wanted to set up a timeout for a future. We want to have any arbitrary future timeout at a certain moment in time. We'll call it a timeout. And it has a future. Because futures are idle, and because, once you drop a future, it's done. It doesn't do any more work. This is super, super easy, right? Here's our future. It's a future. Here's our delay. It's a delay. Cool. We will go ahead and throw some derivatives on this as well, just for fun. Okay. All right. Let's make this into a future. Impl future, impl, where f is a future for timeout. Okay. Our output, well, there's 2 things that can happen. Either we timed out or we didn't. So we will go ahead and wrap whatever this inner one returns in an option, right? If it returned some, we succeeded. If it returned none, we timed out. Okay. What happens when we poll? Once again, the pin comes back. Pin is a little trickier here because this future might need to be pinned as well. Once again, we're going to use a helpful library instead of a bunch of unsafe to make this work correctly, which is called pin project. Pin project creates a function called project on this type, which turns its pinned reference into an object containing pinned references to the inner thing. We can sort of treat it as magic for now and just sort of trust that it works correctly. So we will say let this equals self.project. Okay. So first we pull the future, right? If the future is done, then we're done, right? We succeeded. Match future this dot future dot pull our context. If we succeeded, that's great news. We didn't have to timeout, right? We can return pull ready sum output. Good news. Okay. If we are still pending, that's fine. It's running. Let's go ahead and check on the timer though. Match this dot delay dot pull. If this one expired, it's kind of bad news because we are now going to return ready none. And we know that because futures don't work until polled, because this is going to complete the future isn't going to be polled anymore. This is done. Whatever it was doing, it's gone now. And ideally, when it was dropped, it sort of cleaned up after itself. But whatever happened, it's not going to run anymore. And then finally, if it's pending, that's fine. Our whole thing is pending, right? Here's where the composition comes into play. We have shared our waker with both of these futures. They have both independently arranged to call wake because they want to be polled again, which means that our timeout will be polled again. I find this very cool. Like this isn't possible with sort of the JavaScript promise model because the promise is you set them off and now they're running, right? Now they're totally out of your control. Here, it's sort of all it all composes very cleanly. We can see this. We can just go ahead and see this here in our main function one last time. So we'll go ahead and say, here's our sleep 5, but we're going to run it with a timeout. So we will say let timeout equals, actually, let's go ahead and make a function real quick. We'll make this public. We will say pub function timeout futures, some kind of future, and our delay. Cool. We have our future, and our delay is a sleep. Great. Let timeout equals sleep colon timeout. So our sleep 5 is going to unfortunately time out after only 3 seconds. Okay, and we can't move it. That's fine. We'll go ahead and say match timeout dot await. If it is sum, great, we succeeded. If it's none, we timed out. Should be sleep 5. Great. So obviously this is going to time out, right? Because we gave it, it's too short. So we will see that it runs, it waits, and that's going to time out. Bummer. Of course, we can reverse it, right? We can say sleep for 3 seconds, timeout after 5, run it once more. This time it's going to print success after 3 seconds. There we go. I find this very cool. And in fact, this timeout function, Tokyo provides literally this function. It is a function that takes a future and a duration, wraps it in a struct that I think is in fact called timeout, and literally does exactly what I've written here, except that they use the Tokyo sleep, because the Tokyo sleep ties into the Tokyo runtime. It doesn't require a separate side thread. That's pretty much it. You guys, my audience, the people here learning today, will almost never have to write anything like this, and will almost certainly never have to write anything like this, right? This is what Tokyo does. Tokyo provides these reactors to react to events and provides these future primitives that interact with its runtime that can be awaited. It's my hope that even though you aren't going to be writing anything like this, that this has sort of created some understanding of what's really going on, like why futures have a poll function, what it actually means to await something, and so on.